Hi everyone. In this lesson, we are going to talk about what's called Anova testing. So in the past, we have compared one sample with a value and done a one sample test. And then we've compared two groups with each other and done a two sample test. But now we're going to compare more than two groups with each other. So that's kind of the hallmark. That's why the new type of testing, it's for more than two groups, more than two samples. So for our first kind of example, it says, suppose we had bags of exactly 50 popcorn kernels and we put different amounts of oil in the bags, microwaved each one of them for 75 seconds, and then recorded the number of kernels popped. The question is, does the amount of oil used affect the number of kernels popped? So we would do, if you look over in the chart here, they've got maximum, medium, and none as the different levels of how much oil you're putting in the bag. And it says we could perform three different two sample hypothesis t-tests here. So we could first compare the mean with no oil to the mean with medium oil and say either we think it's the same or we're testing is it not the same. And then we could do another combo. We could do no oil versus maximum oil and see how that works out. And then we would have left to do the medium and the maximum oil together in order to get all of those, every different combo compared with each other. You would have to perform, in this case, three different tests. If you bump it up to 4 samples, you end up having to create even many more tests. So these can spiral out of control fairly quickly if you try this multiple testing method. So what this kind of leads us to is, remember what the significance level actually is. The definition of the significance level is the probability of rejecting the null hypothesis when the null hypothesis is actually true, right? And we usually set that to alpha equals 0.05, although other levels are used sometimes. The problem with this multiple comparison method is that even though the probability of something going wrong on any one of the tests is pretty small, right? We have a small, maybe we set it at 0.05 for each one of these. Well, the probability of something going wrong on any one of them is small, but when you do multiple tests, that creates more opportunities to mistakenly reject the null hypothesis. So even though any one error probability is pretty low, now you've still expanded, but I could make this error. Now there are 3 different opportunities to make such an error. So you open yourself up to a lot more errors when you do this multiple comparison method. Hence the Anova test. Okay, so the Anova test comes from, it's a very strange acronym. It comes from the analysis of variance. So it's the ANOVA, that's where the name comes from. It is a procedure for comparing the means of several groups all at once. It's a more powerful approach than this multiple comparison method would be because it lets us reach the same result with less tests and less error. So this is how we would definitely want to attack these. So the one-way analysis of variance is specifically the Anova test that we're going to be looking at. The one-way Anova test is when you compare means of one variable across several different groups. So it's one categorical variable and one numerical variable. If you look up at the example, that is exactly what we had. We had categories, right? We had the amount of oil, which is a category, and we were comparing that with a numerical variable, the mean number of kernels popped. So we do have that type of a situation, a categorical variable and a numerical variable. And you'll be asked about that in the questions. The null and the alternate hypothesis are the same for every Anova test, but there are a couple different ways that you can write them. So one version of the null hypothesis is to say that there is no association between the categorical and numerical variables. Those things aren't associated at all. So for instance, I could say the amount of oil is not associated at all with the mean number of kernels popped. The alternate that would then correspond to that, if I'm saying that my null is that there is no association, then my alternate would be that there is an association between the variables. So that's kind of the wordy null and alternate hypothesis way of writing them. So then you have a different way that you can write them. So the same thing as saying that there's no association between the categorical and numerical variable would be saying that the mean of the first category is the same or equal to as the mean of the second, which is the same as the mean of the third, so on and so forth, for however many groups you may have. And then the alternate to that would be saying at least one of the means is different. Okay, so you can write the null in two different ways, and they both mean the same thing. They're just different ways of saying that. If the means of all the different categories are the same, then that means it really doesn't, the category didn't matter, right? If all of the means of these maximum, minimum, and none levels, if they all have the same average kernels popped, then it doesn't seem as though the amount of oil affects or is associated with the amount of kernels popped. However, if at least one of those has a different mean, if at least one of those levels of oil has a significantly different average number of kernels that it pops, then that tells us that there is some sort of an association going on between the amount of oil and the kernels popping. So again, you can see those written either or way. You may have to answer questions with them presented in either or of those ways. So I would just kind of know the different ways that you can write those. When you're left on your own to write one, you can write it however you want. Okay, let's do just a couple more questions before we cut and move on to a second video. So the Anova hypothesizing test procedure basically looks like this. First, you will confirm the conditions necessary for an Anova are met and set up your null and your alternate. You will need to determine the degrees of freedom. Then you will compute the test statistic F and the p-value. And then, as always, the same as in our other hypothesis testing, you will compare that p-value to alpha in order to draw your conclusion and interpret the results. If you're going to check the conditions for a one-way Anova test, these are what have to be met. Okay, so there are 5 conditions for an Anova test. First, each population from which the sample is taken has to be assumed to be normal. And so usually that just says it in the problem for us. The samples must be randomly selected and independent from each other. The populations are assumed to have equal standard deviations, or they may say equal variances. And again, most of those things are said just in the wording of the problem. And then your input variable has to be categorical, and the response variable has to be numerical. So you are checking to make sure that those types of variables fit in order for it to be an Anova test.